Yeah, so it's gonna be available for you to watch. So yeah, there's no need to copy the things quite. You can just be following the discussions, and we can just have a conversation about how the questions need to be solved. Yeah, recall that, for example, y equals mx plus c from school is actually a straight line equation. This is actually a straight line equation. All right, if this is a straight line equation, we use this same idea to linearize the equation we have at hand. So how do we do that? Right, we do that by finding the derivative of this.
You
So
are
in other words,
cutting. I don't know if it's my connection or yours.
oh, okay, I'm sort of breaking, right? I'm breaking. Okay, I'm trying to establish just 1 second. Let me see why that would be the case. Am I still breaking? Yes.
Maybe it's because you're recording. No, you're good now. I can hear now. I can hear you now. But
I'm so sorry. Yeah, it might be the network is variant, maybe. It might be the network that is variant. I'm trying to establish, obviously, if there's something I can do to improve that and to make sure that, but obviously,
but I can hear you now.
oh, okay, thank you. Right. So one thing that is very important is finding the derivative of this function, right? So this function f is there. What is its derivative, right? So the derivative of this function can be obtained as follows. So it becomes 5 divided by 2, the square root of x. That is the derivative of the function, simply because the function f written like that can be written as x, 5x to the power 1/2. And therefore, the derivative becomes exactly that one there in use of the power rule. And now we are therefore in a position to evaluate this function at x equal to 9. And that would mean f primed at 9 is actually 5 divided by 2 into the square root of 9. The video is going to be very clear anyway, so I'm going to make the video available to you to watch in case something was not clear and I was breaking up because of network issues. So that'll be 5 out of 6. Okay. Right, so this gives us the derivative of the function, and then we are in business and we can continue solving this. So what is then the solution to this? All right, so moreover, we must be able to determine the value of the function at 9. The derivative at 9 has been determined, but what is the value of the function at 9? The function itself is 5 into the square root of x, which is 5 into the square root of 9. 5 into 3, which is exactly 15. Okay, the value of the function is 15, and we have been able to find the derivative at 9, and those are the things we need, because I must indicate something very important here, okay, that it is this function here can be y equals mx plus c, can be written as y is equal to, okay, it can be written as y is equal to f of a plus f primed of a into x minus a. Okay, so with this, then we are so good, but so good, right? So what is then the implication of this? The implication of this is therefore that we are able to find the results, because we know therefore that y is equal to f of a plus f primed of a into x minus a, which means y equals, okay, the a here is 9, and now the value of the function at 9 is what? Is 15, so we're going to put 15 here. The first derivative, f primed of 9 is 5 out of 6. into x minus the a at which the derivative is computed is 9. And now we are in business, and so y equals, we just multiply through. And if we actually proceed to multiply through, what do we then get at this point, right? So what do we achieve at this point, right? So we continue with this. So what we then achieve at this point is going to be exactly the following. So it's going to be 5 out of 6x, right? And then we multiply out, for example. So that would be minus 5 by 9 is 45. Out of 6, we add 15, and therefore the result is 5 out of 6x, okay? And then we add things up at this point, right? We add things up at this point, and if we add things up at this point, what does this become? As a matter of fact, right, so it therefore becomes a plus here, and then we have minus 45 out of 6 plus 15. Okay, so we just need to add those ones up, and I'm adding them right now. Can just add those in terms of what is 6 by 15. So 3 by 15, this is going to be 90 out of, it's going to be 90 out of 6. So 90 out of 6, 90 minus 45 is going to be 45. It's going to be 45 out of 6. It appears that way. So you then have that this is exactly the linear equation that is required. And we have actually determined the linear equation that is required. And therefore, we're good. We really are so good. All right. So, and then now somebody can say, okay, but this can be simplified because this is exactly 5 out of 6x plus 3 goes how many times into 6, okay? 3 goes 2 times into 6, but 3 goes 15 times into 45. So this can also be written as 15 out of 2. Okay, that becomes obviously the linear equation there. Okay, so in which case, one can obviously ask questions if there are questions at this point. Okay, so you can actually engage and see if there are questions there. All right. So you can have a yes.
The part where you wrote y, the part where you wrote y equals to 15 plus 5 over 6 into x minus 9. I thought that's where you stop. I didn't know you continue in multiplying, and
Oh,
I
I
thought maybe
understand. All
that's
right.
where you stop
All right. Okay. Okay.
with this.
Okay. That is fine.
So you
Once again,
continue in multiplying.
yeah, we continue multiplying. So it is the same. We can stop here, but yeah, we can continue. But then you can have a check. Once again, the video I'm recording, so the video is going to be very clear for you to watch in case the network is failing us. If you check at x equals 9, you can evaluate this equation and write 5 out of 6 into 9 plus 15 out of 2, which is y equals. So this is 5 out of 3 goes how many times into 6? It goes 2 times. It goes 3 times into 9 plus 15 out of 2 is y equals 5 by 3 is 15 out of 2 plus 15 out of 2. And therefore, this is the same as 15 out of 2. The LCD is 2. And then you just add to the top 15 out of 15. 15 plus 15. And this is 30 out of 2. And 30 out of 2 is what? Is 15. Okay, the video is going to be very clear once again. And you need to forgive me if the network is not making the sound quality so good. Meaning y is 15. If y is 15, what did we get the function to be, the value of the function at 9? It was 15. And therefore, this is also 15. And therefore, this is the correct, the very correct result. Okay, this is the correct result. Okay, we move to the next question. Right, the next question is question 2. Right, as a lead engineer at Sasol, you discover that a distillation column is characterized as a dynamic behavior that is governed by the transfer function g of s equals s minus 6 all divided by s squared minus s minus 12. In 2.1, for example, how many poles and zeros does this transfer function have, and where are they located? Okay, so now you're gonna look at the poles, right? So
What are poles? Sorry, what are poles and zeros? What does it mean?
good. So first, yes, we define the poles. What are poles? Well, poles are parts where the function is actually undefined, and therefore, at what points is the function undefined? At what point is the denominator 0? And so for the poles, what we do is we let the denominator to be equal to 0. So let the denominator be equal to 0.
Mm-hmm.
All right, so which means that at this point, if the denominator equals 0, that would mean s squared minus s minus 12 equals what? Equals 0, right? So because that is the denominator there. So which means here you then have the factorization to do. What are the factors here at this point? The factors of s squared, s and s, they are factors of minus 12 that give, that give minus 12. So which means that at this point, you would have actually 4 and 3. All right, so this will be minus 4 and this will be 3. And then we have that. So these are, okay, we need to just work on these factors a little bit. These 3 must be plus. Okay, these 3 must be plus. So, which means, therefore, what do we have here? We have, therefore, that s equals 4 or s equals minus what? Minus 3. And now that is actually, these are the poles. Okay, so the conclusion, therefore, becomes simple. And we say then hence the transfer function, right, the transfer function has 2 poles. Has 2 poles located at s equals 4 and s equals minus 3. Those are the poles of the function. And then the next thing we obviously discuss is the idea of what you call the zeros of the function. What are zeros of the function? Well, zeros are the points where the function equals 0. And now you let the transfer function g of s be 0 to find the zeros. And that means, therefore, you have s minus 6 all divided by s squared minus s minus 12, and this becomes 0. Okay, when you let the function to be 0, we actually, what does this mean in mathematics? Okay, when the function is 0, it actually means that the numerator must be equal to 0. Right, and if the numerator is 0, it then means that S is identically 6. And if S is identically 6, what do we then get? So we then get that S is 6. And the conclusion is that thus the transfer function has 1, 0, namely S equals 6. Okay, so we have got 1, 0 there, and it is exactly S equals 6. Okay, right. We continue.
Okay.
Right, so now we've found the zeros and we've found the poles of the function. And then we just need to compute now the output response for unit step change. Okay, so we're going to actually compute the unit response for unit step change. And we continue to do that one. Right, so we're going to do question 2.2. What is the output response? Right, so we look at the output response. Right, so the output response at this point is given by the following diagram. So you need to have the input. If the input is given by R as a function of t, and so you have L, which takes the function R of t to, which is the Laplace transform, which transforms it to R as a function of S. Then the next thing is we would have here in the block something we call the linear time. Right, so we would have here in the block something we call the linear time of the invariant system. Right, so we put the linear time here, linear time of what we call the invariant system. Okay, right, so with that linear time of the invariant system, we're going to proceed to the further right of the diagram. Okay, but now we note that this obviously diagram has the tendency to proceed further to the right. So if you have that input that gets into the linear time invariant system, you'd have something we call the output. Right, so the output is actually C of t. And the linear C of S, okay, which is the linear there. Okay, let me just write this clearly. So this becomes therefore the linear. Right, so which becomes C of S.
Um.
Yes. Hello?
Hi.
Yes.
Yeah, I can hear you now. It got disconnected again, I think.
I'm so sorry.
Yeah.
Okay, well, yeah, once again, the video is going to be very clear. Okay, I know the network can fail us, but the video is going to be very clear because I'm wondering why it's breaking. Because it should not at all be breaking. It shouldn't. Yeah, but I'm hoping that, well, the video is going to be excellent. I'm going to send you the link to the video at the end of the lesson. It will take me 30 minutes. It will take me 30 minutes to upload the video because I'm going to get the video from Zoom. Okay, so that is the thing there. Okay, that's the thing. I'm going to get the video from Zoom. All right. Right. So let's do this. Okay, we continue. We continue just now. the contagious now. All right, so there's something we call the fact that the initial conditions will give us the transfer function. So, in other words, the transfer function can be seen as L of the output, all divided by, which is the Laplace transform of the output, divided by the Laplace transform of the input. Right, which means the transfer function is going to be C of S divided by R of S. Okay, so at this point, we are given we are given the transfer function, right. So we're given the transfer function. So given the transfer function, right? Given the transfer function, what do we have? Right, it can get disconnected. I'm so sorry if it does. It's a network issue.
Okay.
Right, given the transfer function, the video is going to be excellent because the video is being recorded from the sound I'm giving. So it's going to be so excellent. Right, so you note therefore that the input of the, okay, given the transfer function g of s, given the function g of s, which equals given the function g of s, which equals s minus 6 all divided by s squared minus s minus 12, which is like that. Okay. There's something we call the response of the system of unit step, right? But also the input of the system, the input of the system R of t in terms of the unit step. We apply the Laplace transform. We apply the Laplace transform. Right? If we apply the Laplace transform, we have that R of s is 1 over s. The response of the system response.
Sorry, in the Laplace table, the table.
Okay, the Laplace table.
Oh, the 1 over s is, we take it from the Laplace table.
Yes, we take it from the Laplace table, the 1 over s. Yes. For the...
Oh, is it written that rs is equals to 1 over s on the table?
Yes, it is. It is here. Okay, so in other words, if you have a unit here, 1, a is 1, then it becomes 1 over s. Because it is a and then it becomes a over s. But if a is 1, then it becomes a over s. But a is 1, so it becomes 1 over s.
Oh, okay.
Yeah. All right. So which is exactly R of s is therefore 1 over s. Now, we then continue. We then continue as follows. And see that the response of the system of unit step is C of s, which is R of s multiplied by G of s. Right, so you can write this as follows. So you can write it as y of s, which is the popular way to write it, is equal to the r of s. You can write it as r of s, which is and then times g of s, or you can write it as g of s. Okay, you can write it in two ways. This doesn't matter. You can write it as c of s equals g of s times r of s. C of s. What is g of s? Okay, so obviously we already have the transfer function. Okay, so I'm just going to copy that in. G of s is exactly s minus 6 all divided by s squared minus s minus 12 multiplied by the 1 over s. Okay, so now this is C of s minus 6 divided by s minus 4, factorizing the denominator into s plus 3 multiplied by 1 over s. Okay, and then now this means that you can write this one as that. As said already, sometimes it can just be written as like that. You can write like that. Okay, C of s. I would like to write it as C of s here. Like I can write it as y, because no matter functions are called f, y, and so on. Okay, doesn't really make a huge difference. So, which means you have that. This we can write it as 8 divided by s minus 4. You can write it as b divided by s plus 3. You can write it as c divided by s. Okay, this here is
Okay, where
the.
does the A and B come from?
Please come again.
Where does A and B come from now?
Okay, yeah, A and B. That's a good question. So A and B, they're coming from something called using partial fractions. Okay, so in other words, we can split this into what we call partial fractions. Partial fractions are part fractions. So you'd have A over the denominator, B over the second factor of the denominator, and C over S. Okay, so those are just part fractions we call partial fractions, and we shall be doing lots of them in this course. Let's just do it here. So the implication therefore becomes that we have, for example, we have that a divided by s minus 4 plus b divided by s plus 3 plus c over s is equal to s minus 6 all divided by s minus 4 into s plus 3. Okay, so these things are equal to each other. In other words, this is equal to this, but we just have separated them and want to get the values of A, B, and C that will make this decomposition possible. Okay, it's called decomposition, just break it apart like that. Okay, so if you multiply through by the denominator, this is going to be A into S plus 3 times S. You multiply by the denominator of the right. You have b into, you multiply by the denominator, so it's going to be s minus 4. You multiply by the denominator, so it's s minus 4, s plus 3, which is s minus 6. So now at this point, you can multiply these out. Right, so here you multiply out, so it's going to be as squared plus 3as plus bs squared minus 4bs plus c okay, we're multiplying out here. So s by s is s squared. We'll multiply by the c, and then you multiply s times 3, which is 3s, minus 4s, which is minus s, minus cs, minus 12. C, okay, is equal to s minus 6. Okay, all right. If you're breaking, if
Sorry,
you,
can you go up? Can you scroll
okay,
up again? Scroll down on
all right,
15.
all right.
From here, the y where you wrote using partial fractions, ne? And then
Yes,
you wrote the a, b, and c. What
yes.
happened to the s minus 6, the one that was in the numerator? You
We always
it,
we leave it out. We leave it out, but it's gonna be taken care of by the values of a, b, and c. It's gonna be compensated. So the a, b, and c will contain it. We'll bring it up. Yeah, because we need to
okay,
find. Yeah, we need to find the values of a, b, and c that will bring the numerator. So always leave the numerator out. We focus on the
okay,
denominator, and then the a, b, and c, because they are actually numerators, they will make it up. So when we add them up, they will give us s minus 6. Somehow it works. Okay, so this is called partial fraction decomposition in particular. Okay, right. So
okay.
I'm
So
gonna
here
now
where you multiplied by
I multiplied by this denominator, this one here. So we multiply everything by this denominator. The aim
oh,
is to get rid of the fractions and now write the whole thing without fractions. And in the paper, this step here, we've written without the fractions. We sort of cross multiply, if you like. If you cross multiply like this denominator that contains all of them, all the s minus 4, the s plus 3, and the s. Now, if you cross multiply, it will come this side and multiply each of these.
okay,
And this is what you get. But obviously, the denominator, now the s minus 4 into s plus 3 into s, if it multiplies like the a part, so only s minus 4 is going to disappear, and we're going to be left with s plus 3 and s. Okay, that's why I have s plus 3 and s. Okay, if it multiplies the b part, s plus 3 is going to cancel out, and you're going to be left with s minus 4 and s. If it multiplies this one, it's going to cancel out the s, and you're going to be left with s minus 4 and s plus 3. Okay, so yeah, that is just simplification. Just take note of that. So at this point, what are we then getting? So what we're getting at this point is the following. So we're going to group. Let's group. So it's going to be a plus. So this quadratic, it has an s squared, and that is quadratic. So it is a plus b plus c. And then we have s squared, right? So we have dealt with, we're just grouping the terms. And then there are terms that are called linear terms that have s in them. So like this 3a. Okay, there are many ways to do this, obviously, but I sometimes prefer this method. You have minus 4b, and then there is cs, which is minus cs. And then you have minus 12c. It appears that there's only one term that has no letter s in, and then you have s minus 6. Okay, right, so let's continue with this here. So the implication then is that you will have, for example, a plus b plus c is equal to 0, because there's no quadratic. We compare, so we say comparing coefficients. Okay, so what we'll be saying, okay, but where are these things coming from? Okay, we'll be saying comparing coefficients. Comparing coefficients, so you're going to have that a plus b plus c is 0, because there is no s squared on the right. Okay, but then we also have the 3 We also have 3a minus 4b minus c is equal to the linear one. The coefficient of s here is 1 on the right. And then what else do we have? What else do we have? So we also have the last one, which is minus 12c
Let's see.
is equal to minus 6. Okay, the constants are equal. All those constants, and then now we continue. Here in the last one, we can divide through by minus 12, meaning c is minus 6 divided by minus 12. Negative divides 6 over 12 is like 1/2. Okay, because 6 goes 2 times into 12, and the negatives cancel out. All right. Once we're here, okay, we just need to use the other equations to get the results, and then we are good. So we can use this one here and substitute into this equation and substitute into that equation and see what we get. Like in the top one, we shall have that a plus b is equal to, if you put c equals 12, 1/2, excuse me, so you move it to the other side, it's going to be minus 1/2. And then if you continue like that, and then here, you would have 3a minus 4b. You put 1/2, which is 3 over 2. Okay, so at this point, you have a plus b is minus 1/2. Okay, so we can multiply it through by 4. If you multiply it through by 4 on the left and 4 on the right, which is 4a plus 4b. And then this is 3a minus 4b is 3 over 2. If you add these two equations, you add them together. Okay, if you add them together, what do we get? So if you add them together, you get, for instance, 7a is equal to, you get 7a is equal to, so you'd have this one here is this one here is equal to what? Okay, minus 2 and 3 over 2 is minus 1/2. And then if you divide through by 7, you'll get minus 1 over 14. Okay, so that's what we get. Okay, we continue. All right, so we have this, and then now we can get, so we just got,
Can I interrupt?
yes, please.
Comparing coefficients, I see what you did here with those three equations, and then we got C, and then you substituted C, the 1/2, on the second equation and the first equation, right? And
Yes,
then the one written in blue, A plus B equals 1/2. Which one is that one? Is it the first one, negative
yes, it
one
is
over
the,
two? Oh,
yes, the one with negative 1 over 2 is the first one, is the
okay.
green one. But now we just multiplied it by 4 both sides.
Oh, and the 4AB.
And the 4a and 4b, it's multiplication. And yeah, so this one here, Okay, that's a good question. Why did I use 4? Because I want to cancel the b's. Because
okay.
this one has 4b.
Okay.
Okay. Okay, what do you think?
I'm just still reading.
Okay, that's fine. Okay, think about it. All right.
Okay, wait. Oh, okay, I see now. And then you use the other equation, the 3a minus 4b is equal to 3 over 2. Which one is that one? Oh, you
Uh-huh.
added.
Yes, I added. I added. Okay, I know that it looks messy a little bit. These equations are like many, you know. Okay,
Okay.
right. So, but now we got that A is that. Okay, so I can use any of the equations to get B, like using the equation A plus B okay, using what? Using like the first one, the red one, A plus B plus C equals 0.
Mm-hmm.
Okay, so A plus, so our B is what? Okay, is what we want. So, but
Yeah.
we have our A, our
Minus
8
1 over
minus 14 plus B, and
yeah.
then C is,
1 over 2.
yeah. So we just need to get B here.
B
Okay, we
is
continue.
minus B is minus 3 over 7.
Yeah. So what do you think B is? B is
It's
minus 3 over
positive 3
7.
over minus 3 over 7, yes.
Well done. Okay, that's correct. All right. Okay. Okay, we'll continue. Okay, we'll continue then. All right. Okay. Okay, so we get that B is minus 3 over 7. So with this, okay, hence, what is then the conclusion out of all this? The conclusion out of all these is therefore that we've got that C is 1/2. So it means therefore we can write that y of s is equal to a over s minus 4 plus b over s plus 3 plus u over s. So what is our a? We got minus 1 over 14. 1 over s minus 4. Our b, what is our b? Is minus 3 over 7, which is 1 over s plus 3. And then s is c, excuse me, is 1/2. C is 1/2 into 1 over s. which is now you take the inverse Laplace transform. So you have this, and then you have minus 3 over 7. You take the inverse Laplace transform of this, 1 over s plus 3. You take the inverse Laplace transform which means the inverse Laplace transform of this. Okay, what is the inverse Laplace transform of s minus 4? So use the table. All right, so you're here. So if it is s minus 4, then you have like s minus b, and then it is e to the b. So you'd have minus 114 to e to the 4t, for example, like that. So even here, we can just change this. Right, so the inverse Laplace transform of y of s becomes y of t. Right, and then we continue with the inverse Laplace transform, so you can move this one a little bit to the margin. So you have y of t here, and then this is minus 114 e to the 4t. And then now there is s plus 3, so it's the same, but now the s plus 3, you can write if it's 1 over s plus 3, you can write it as 1 over s minus into minus 3. So that is exactly the same, it is the minus there, but then the b is going to be negative. Okay, so it's going to be minus 3 over 7s to the minus 3t. Okay, and then now, but I want to add something to this. Okay, we add something to this. So, right, let me just add the unit function. Right, so you put the unit function, which is the Heaviside unit function. So you have this one here, and then you have e to the minus 3t. You put the unit function because it has to do with the unit function according to the question. And then the last one, what about 1 over s? 1 over s. So 1 over s is like the top is equal to just 1, but now just 1/2. So you have 1/2, and then you multiply it by the unit step function. The implication, therefore, is that this y of t can be written as minus 1 over 14 e to the 4t minus 3 over 7 e to the minus 3t plus 1/2 u of t. Hence, a unit step change has the output response that. The conclusion, therefore, is that hence the unit step change has the output response. What is the output response? It is y of t equals minus 1/14 e to the 4t minus 3 sevenths e to the minus 3t plus 1/2 into the unit step function. Okay, so we have answered that question. So this question here is the one for the unit step change, right, for 20 marks. Okay, right, so we continue to the next one. Right, as you continue practicing, I'm going to bring more questions on Laplace transforms today. Okay, so let's look at question 3, for example. Question 3 is saying find the Laplace transform of this function. So that's pretty straightforward. So we look at question 3 now. Right. So question 3 is about the Laplace transform of that. So in 3.1, we have f of t, which is 1 minus cosine of omega t. We have L of t now, which is L of 1 minus cosine of omega t, which is f of s. Okay, so now this is the Laplace transform of 1 because the Laplace transform distributes over sums and differences. So it's going to be cosine of omega t. Now this is f of s. What is the Laplace transform of 1? Okay, this is what we said here. So if it is 1, it is 1 over s. So for the unit, it's just 1 over s. Right, minus, what is the Laplace transform from the table of the cosine omega t is like cosine of at is the same as this one. So is the same as s divided by s squared plus omega squared. Then, and that is the answer. In other words, the conclusion is therefore that hence the Laplace transform of f of t, which equals 1 minus cosine omega t, is given by f of s, which is 1 over s, minus s over s squared plus omega squared. Okay, so we have answered that question. And that was question 3.1, which is find the Laplace transform below. Now the next question is about the dynamic behavior. So find the dynamic behavior of the system, this one, when there is an input change of f of t equals t squared. And then let's compute the dynamic behavior. Right, this lesson is being recorded, so please you'll get everything. The sound quality will be so good because it is recorded on my device. Okay, so there cannot be network issues.
Okay.
All right. Here, yeah. So in 3.2, then you'd have that given the system, right, we have been given the system y of s, which is divided by f of s, which is 2 over s. Right, when there is an input change, we note that when there is an input change of, right, so the input change here is f of t equals t squared. And so, what is the meaning of all this? What is the meaning of all this? We have that we can be able to find the Laplace transform of f of t, which is the Laplace transform of t squared. What is this? This is f of s. That one of t squared, what is the Laplace transform of t squared? So we know that one. We go to the table. Right, the Laplace transform of t to the power n is n factorial over the n plus 1. So this one is going to be like 2 factorial divided by s to the t to the 2 plus 1. Okay, so in other words, the implication therefore is that f of s 2 over s cubed So we have got f of s, so that the dynamic behavior, okay, so that we come to this equation. This equation is clear. It says this. So it says y of s is basically divided by f of s, and this is equal to t of s. So it means, therefore, you have y of s divided by, what is f of s? It is 2 over s cubed. And then this is 2 over s. So you can just cross multiply this one. If we do like this, so it becomes y of s is 2 over s multiplied by 2 over s cubed. And then this is y of s is 4 over s to the fourth power. So it means, therefore, you can find L inverse of y of s, which means L inverse of 4 over s to the fourth power. So we're getting the inverse Laplace transform now. And then,
Okay.
what is the inverse Laplace transform of this? So it means you have y of t is equal to, what is the inverse Laplace transform of this? Okay, so you continue. Hello, good morning. Fine, thanks, and you, my friend? Yeah, that's fine. Is it possible that maybe you can give me a call at 10:30 when I'm free, because I'm in class now? Okay, thank you. Thank you so much. Okay. All right. So that was my other student anyway. All right. So he wants to learn now, I'm sure. Right. So y of t equals this. Now, y of t then is the inverse Laplace transform of 4 over s. Okay, this 4 over s is very much reminiscent of the following. It's very much reminiscent of these things here we have been seeing, but yeah, the power, the t to the power. Right. For example, it is very much reminiscent of t to the power n and this one. But let's see now. You must have n for t to the power n, it must be n factorial over s to the power n plus 1. So at this point, this must be the same as what? So if it is s to the fourth power, you need one less. So it's s to the fourth power. I can write it like how? Okay, I can write it like plus 1. So it must be 3 plus 1. Okay, so you must break it down like that. It must be 3 plus 1. And then the numerator must have like 3 factorial. And then you take out the 4 and then you divide by 3 factorial. And then you put the inverse Laplace transform. Right, because now this is all good.
Why did we use 3 factorial?
I use 3 factorial because the formula says there must be n factorial.
Yes.
So
and then
yeah, there
n
must
is
be n
equals to 1, 2, and 3, etc.
Yes,
Right?
because now the power 4 factorial can be broken down into 3 plus 1, because it must be a number plus 1. And 4 is like 3 plus 1. And then
Okay.
in the numerator, then you put the n factorial. But now we changed the whole thing because it was 4 there. So a number can be put out of the inverse Laplace transform operator. So I put out the 4, and then now I've divided by 3 factorial, and then I've put a 3 factorial at the top, because then the 3 factorial cancels the 3 factorial. And then this means you have y of t equals 4 over 3 factorial. What is the inverse Laplace transform of 3 factorial over that? So if you have this, n factorial over that, it becomes t to the power n. So at this point, what does it become? So it becomes t to the power the n, and the n is 3, like the n factorial. It's like 3. So it's that one. And then now, what is all this? So this is y of t equals, what is 3 factorial? 3 factorial is 3 by 2 by 1, which is 6. T cubed. You can just write it like that, but yeah. Okay, 2 goes how many times into 4? It goes 2 times, 3 times, and this is 2/3 t cubed. Right, so now we make the following observation here, that since I can write therefore a conclusion, right? So therefore since the dynamic behavior is the time dependent, response. It is given by y of t, which is 2 over 3 t cubed. Right, so that's what you get. Y of t equals 2 over 3 t cubed. Right, so we're done because the question said find the dynamic behavior, and this is the dynamic behavior. It is time-dependent response, and this is a function of time. It's y of t equals that. So it is time-dependent, and we're done. The next one is differential equations. How do we do differential equations and other related notions? Solve the differential equation, this one. Right, so we have the differential equation, t squared y dt squared dy dt, and this is e to the minus t. This differential equation is given for y of 0 equals y prime of 0 equals 0. So what is all this here? Then we get the L. So to solve the differential equations, we use the Laplace transform. Is the easiest one to use. So just take the Laplace transform L of the left-hand side, which is d squared y dt squared dy dt. We have taken L of the left-hand side, and then we have taken, now we take the Laplace transform of the right-hand side. Okay. Now this here can be seen as the Laplace transform of this. So this one can be seen as y of t double prime plus the Laplace transform of the single prime of y of t, and then the Laplace transform of e to the minus y. Okay, we use the table now. Use the table. So this one here is what we use for the double prime. So it means that Laplace transform of double prime for the differential equation is s squared, because it is f in the question, but here we're going to use y. So it's going to be y of s, not minus s, f of 0, minus f prime of 0, plus. What is the first derivative? Okay, it is the one at the top. So it is exactly s, y of s, minus, anyway, I just called it f, but please, let's just call it y here. Right, so it is y, And then even here in the place of f, we're using y because the differential equation has y, although the rule has f. Obviously, just time symbols this. Right, so here we have minus f of 0, which is minus y of 0, which is equal to L of e to the minus y. Okay, so now we use the Laplace transform for the e part. Okay, so what is the Laplace transform of e to the minus y? So e to the bt is 1 over s minus the b. So it's going to be 1 over s plus 1. Okay, we are good. Okay, just something here. Okay, these are equal to each other. These are equal to each other. And they're both 0. Y of 0 is y primed of 0, which equals 0. So which means s y of s minus s. This is 0. 0 plus s y of s minus 0 is equal to 1 over s plus 1. So s squared y of s plus s y of s is equal to 1 over s plus 1. So we pull out y of s, which is s squared plus s, is 1 over s plus 1. Okay. Now we just make the y of s the subject, so it becomes 1 divided by s squared plus s into s plus 1. Now we can just do factorizations. Y of s is equal to, what are the factors of the s squared? It becomes s into s plus 1, but there's already s plus 1. This becomes 1 divided by s into s plus 1 all squared. Now this, here we can be able to, for us to get this, we must use the partial fractions like we did before. So using partial fraction decomposition, using partial fraction decomposition. Okay, so it means y of s is the same as a over s plus b over s plus 1 plus c over s plus 1 squared. So, and the implication is clear. It is the fact that a over s plus b over s plus 1 plus c over s plus 1 squared is equal to 1 divided by s into s plus 1 squared. So, which means now if you multiply out by the denominator, it becomes a into s plus 1 squared plus bs into s plus 1 plus cs is equal to 1. Okay, what is all this now? We're in business now because we can just be able to get this right. So it becomes a into, let's square this one. This one becomes s squared. S by 1 by 2, it becomes 2s. You square the 1, it becomes 1. Plus, you multiply out, which is bs squared plus bs plus cs equals 1, which is a squared. Okay, we'll continue. We continue. So you have this one plus a to s. We can write it like this, which is 2as plus that. So which is plus b squared plus cs equals 1. So which means you have a plus b, 2a plus b. You dealt with this ones, you dealt with this, the b, and then you must deal with the c. So you must just say here plus c. And then here, which means a plus b is 0. And then we're comparing the coefficients. By comparing coefficients, which means a plus b is 0, which is 0. Okay, so which means that b is equal to minus 1 if you put the a there. So that we have 2a plus b plus c equals 0. There's that equation. But you already have 2 into 1 minus 1 plus c equals 0. 1 plus c equals 0 minus 1. So which means you have y of s. So which means y of t s plus 1 c over, and a is 1 over s, c is this. But if you add all these things here, it gives back that what we had. So the implication is that for L inverse is that y is the function of t is okay, so here this one is still y of s. Still y of s. Doesn't matter, we can use the same color. Y of s. So this is 1 over s minus L inverse okay, so okay, we continue. Okay, continue. Sure. So the L inverse, we saw that the L inverse of 1 over S is 1. Okay. And then this one is e to the minus t. Just put a minus associated with the 1. And then this one of the square is here. If it is S plus 1 squared, so this one minus 1. So it's 2, which is 1 plus 1. Okay, so it's 1, it's like that. So it's like S into minus 1. Right, so if that is the case, the inverse Laplace transform is going to be this. So what does this mean? Then it means t to the power of the n, which is 1, e to the power of the b, which is minus t. So which is minus t e to the that. Therefore, the solution to the differential equation is given by that. Therefore, the solution to the differential equation is given by y of t is equal to 1 minus e to the minus t, e to the minus t. Okay, obviously this solution can also be written as 1 minus, so you can pull out this is a solution as required. Is required. So we have been able to solve this differential equation. Okay, now you can check your differential equation and whether it's quite a very, very accurate answer by using, for instance, the initial values. Right, can do a quick check. Right, so using quick check, y of 0 is 1 minus which is 1, and this is 1. Y of 0 is 1 minus 1, which is equal to 0. So obviously we have here that y of 0 is equal to 0 in that. So it is the case there. Okay. Right, so we have discussed that. And then I'm going to look at other practice problems that we need to go through. For example, here's another practice problem that focuses on sketching functions. Like, it is expected of you guys to be in a position to, in engineering, to be able to sketch functions. Like, if you need to sketch the function f of t, how do you sketch this function? So we're going to look at the graph of this function. Okay, we're going to look at the graph of the function. So if this one, for instance, is like a y and a t, you can be able to sketch this. How do you sketch this function? Right, to sketch this function, you're going to start by maybe sketching this one here. Right, so to sketch this function, you can sketch it like this. If t is 0, then y is 2. If y is 0, then t is what? T is 2. And then you're going to have a function that cuts through 2 and 2. But this function is going to start from 0 to 2. Right, so it's going to start from 0. So to 2. And then, okay, at 0, it is included. Because when t is 0, you have 2. You put 0 here, it becomes 2 minus 0, which is 2. And then when t is 2, 2 minus 2, you have 0. So you have y equal to 0 at 2. And then now you can sketch the function. So this function becomes a straight line like that. Okay, so we've sketched a function between 0 and 2. Now, there's another function that you sketch between 2 and 4. But now that will be the t-squared part. Right, between 2 and 4, you have the t-squared. What is the graph of t-squared? So the graph of the t-squared is this, is a parabola like this. Right, so if you pick just a portion of it between 2 and 4, it's going to be like that. Right, so, but what is the parabola when t is 2? Is 2 squared? What is 2 squared? It is 4. So when t is 2, we have that y is 4. And then when t is 4, like that. So this one is the 2 minus t part. So this one is the 2 minus t. This one is the t squared. And then now there's another one when you, so this is, at t equals 4, once again, you'll have like a 16. Let me just, at t equals 4, then you're going to have like a 16. Okay, now from at t equals 4 here, then we have minus 3. Okay, and onwards. So, okay, when t is 4, then y is minus 3. When t is 4, then y is minus 3. Goes on and on and on. Like that. Okay, so those are the kinds of things that you need to be in a position to learn. You must be able to sketch the function like that. All right, because if you sketch the function like that, then you are surely in business. Okay, and then you can be in a position to understand things very, very well. Okay, right, so you're there and you're good. Right, so the couple of things then that you need to as well consider. Okay, I'm going to look at the Heaviside step function, but I wanted to do computations of differential equations like this one. Okay, we have seen questions like that, but we shall do this one now. And then we shall do, okay, I'm going to load more questions. Did I load more? I didn't, okay. Okay, let's practice with this one for now. Okay, this we've already seen, but it's like the previous question. Like you need to be able to solve the differential equation like that. I'm going to load more questions, which is theta double primed 6 theta plus 10 theta is L of 4t minus 2. And then now you're going to distribute and have 6. And have 6 into this. Plus 10 theta. Oh, L of D. What is these double primed? Okay, we saw that one in the table, so we're gonna just use the table so we wrote it here as well, so we can just use what we used here in the green part. So this one is gonna be, for instance, like an S squared, always S, right? Then we have capital theta, S. I'm looking at the green part because we took it from the table, and then S. Then you have small theta, it's 0. And then you have, look at the green table, you have the primed, 0, plus 6. Then you come to the 6, L of theta primed. So from the table, it's going to be S, big theta S, small theta 0. And then plus 10. What is L of theta? It's big theta of S. 4 into. Right, so what is L of the delta minus 2? Okay, this one you need to just consult the table. Okay, here is delta of t minus a. So delta of t minus a, so if you find the Laplace transform of delta t minus a, that Laplace transform is e to the minus as. So if it's e to the minus that, so if it's e to the minus as, let's just come to that one. So it's going to be e to the minus 2 s. Okay, so just note that one. So what is this? 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 Okay. All right. So now just substitute everything. Just plug in the 1 and the 0. So this is s squared. Big theta of s minus theta of 0 is 1. Okay, this one is the primed. Theta primed of 0 is this one, which is 0. Multiply through by the 6 here. And theta of 0 is 1. And put the brackets in the meantime like that. Goes 4 e to the minus 2s. Plus 6s theta of s minus 6 plus 10 theta of s equals 4 e to the minus 2s. So what is all these here? You can pull out this one, the big theta of s is s squared plus 6s plus 10 is equal to 4 e to the that plus s plus 6. So this is theta of s, which is equal to 4e to the minus 2s plus s plus 6 s squared plus 6s plus 10. So we just need to solve the differential equation. And what do we do here? We take the inverse Laplace. But you watch out this, is it ideal? Okay, so a couple of ways to do this. And I'm going to demonstrate other methods of doing this, okay? So if this is the case, I'm also going to use an app. There's an app I also use to do this. Okay, so I'm going to demonstrate that an app can be able to do this so that you can be able to check your answers with the app, you know. Right, because now this you can break it up. Which is s squared plus 6s plus 10, which is s plus 6 divided by s squared plus 6s plus 10. Right, so now let's look at this. Now, these can all be done. What is the Laplace transform of e to the that and s to the that? Right, so to do this Laplace transform, you'll have to, you need to break this one apart. Right, to break that one apart, you need to use, and you can use the 10 the denominator be factorized, what are factors of 10? Okay, and also here, so this will be theta of s is 4e to the minus 2s, which is s squared plus 6s plus half of 6 is 3 squared. Well, half of 6 is 3, but you square it, and then you subtract the square, and then you add 10. This is when is that? Plus 10, so we can write it like that. So which means theta of s is 4e to that. Okay, the same as what it's in the right, but we're doing a different problem. So this is s plus 3 squared. 10 minus 9 is 1. And then here we have s plus 3, which is s plus 3 plus 1. Okay, now you refer to the table again. If it is s plus 3 plus 1, what is this? Okay. We can write it this side so that I can have the, so you'd have theta of s is 4e to the minus 2s, all divided by s plus 3. Okay, I'm going to bring the table now. Let me just compare with the table, and then, but also I'm going to teach the use of the application. There's an app that is used to do this. Right, so, which is faster. Right, so for example, if you have, let's see this table here. Okay, if you look at this table, something like this. Right, so if you look very carefully, you can be able to see that. Okay. So this one here is the following. Right, so this one is going to be theta of s is equal to 4e to the minus 2s, all divided by s plus 3 squared plus 1. This one is looking like this one of the e to the bt cosine 80. So you can write it as s minus. You can write like the s minus b, but it's plus. So you put minus 3 like this. S minus into minus 3. A plus 1. Now what do? You take the inverse Laplace transform. So which means that theta of t is the inverse Laplace transform of the theta of s. So which means theta of t is the inverse Laplace transform of e to the minus that divided by s plus 3 squared plus that plus the Laplace transform of s minus into minus 3 divided by s minus into minus 3 squared plus 1. Can I write this one at the bottom? Right, so you have this one plus. So you have the inverse Laplace transform of s into s minus 3, s minus 3. Okay, so we have this, which means theta of t is this. Right, so you need to do the Laplace transform. So the Laplace transform of the other one is exactly, this one is like plus 1 squared. So it is b. So b, here the b is what? The b is minus 3. The a is 1 here. And then what else? Okay, we're done. So which means that it is e to the minus 3t cosine t, because the a is t. So what do we get? Right, so we get that one. Now we have to do the other part. The other part can be done by using obviously the tables, but also you can use any of these results, like that result there. How does that look like? So I'm going to use, I'm going to show how to use the applications, but also I'm going to obviously give the result. Okay. For example, if you have 4 into that, into that, into that. So are with you now? I'm here. Okay. The other one, it resembles that. I'm going to teach you how to use an app. There's an app we're going to use to do the calculation. So if it is the squared plus 1, it is the squared plus 1. Okay, so as a consequence, obviously, it actually would resemble exactly this part here. So this would be the unit step function or the Heaviside step function of t minus 2, because it is t minus c. And then now you have f of s. And then that would be the Laplace transform of the other one. Let me see, of the sine function. But it is the sine function, sine, for the sine of t minus 2 All right, so that becomes the result. So which means T of 2 can be written as 4 times the Heaviside step function at 2 for this times the sine of T minus 2 plus e to the minus 3t cosine t. Okay, now for example, this one here can be done by using the Heaviside step function, and can be done by using the application. There's an app we use. If I can demonstrate that one. Okay, using the Symbol Lab app, for example, let me see if I can do this. Can't go to. I want to add something else. Okay. I'm gonna mess things up. Right. So, okay, just 1 sec. 1 second. Okay, I'm gonna collapse this one. Let's see, just 1 sec. I'm gonna collapse this template. And then I'm gonna use this one. Okay, so I'm gonna bring this app here. Okay, I want to just show how to use the app. Okay, because it's computerized, these things. You can check your answers here as well. So, for example, okay, there's something called the Symbol Lab app. So the Symbol Lab app can be able to do this. For example, let me start by doing this one. So this one, you come and say the inverse Laplace transform. Inverse. See, it appears not to quite be compliant. Let's see, inverse. Inverse. Okay, if you type Laplace, see, it's something I want to show you. Why is it? Doesn't want to take A? Okay, just 1 sec. I want to show something here. You can see that it is not quite accepting. It is not quite accepting. Okay, let me just go to the app. Just 1 minute I want to conclude the discussion, but I want to use this application to. Is this one? Didn't want to work, but yeah, I want to demonstrate how to use the app. Okay, it's rotating. If you want to work the other way. Okay, just 1 sec. If you can just be able to because it might be rotated to a screen. Okay, but I want to say that you can do the Laplace transform of this by using this application. Okay, so like if you do this, for example, want to say okay, it wants to do this, for example. Right, if you have like you want to do the inverse Laplace, so you type inverse. Okay, but it could not accept when I was on the other divided screen. And then now you have, for instance, you can do s plus 6 is one of the things that one of the Laplace transforms we did. And then in the denominator, you have that one. see. Okay, so anyway, which is s squared. Okay, s squared plus 6s plus 10. Okay, let's do the inverse of this. So, in other words, the inverse Laplace transform of this is exactly that one. For example, okay, so just take note of that. So the inverse Laplace transform of this is exactly that one. Just one sec. Yeah, just note that because I'm getting back to that. I'm just using the application to check this. And then now you do the other inverse Laplace transform. Okay, so there's another inverse Laplace transform of the numerator. I'm going to get back to that screen. So it's 4 exponential minus 2s. All right, so you can always check your results here. Right, so you have this. And then you have s squared in the denominator. You have s squared plus 6s. Okay, plus 10. We have these. Right, which is exactly the thing we got. Okay, which is exactly this one. Your screen might have rotated, but you'll just bear with me. And I'm gonna switch back. Right, so now, where am I now? Okay, just one sec. Right, so I'm right back to the other screen. So you here, here, let me see, we here. Right, so that is what we were. And then now I want to include that other screen. Okay, where maybe I'm gonna get back. Yeah, good. I got back that screen. So I got back the screen here. Got back that screen. Okay, I want to add something here. As I conclude this one, I want to add something here. For example, okay. See. What is this now? Let's see. So this is S plus, okay, I'm just comparing here, just to conclude my discussion. Okay, I'm comparing just these two. Okay, this one is S plus 6, okay, which is the original question. Okay, so obviously here, I actually had to write it as the plus 3 because it's plus 3 plus 1. And then the 6 can be written because it's plus 6, or I would like to write a plus 3 here. Okay, just one sec. So, let me see now. Okay, so because, okay, this came from the other side. It came from here and I moved it to the other side. Okay, I'm concluding the discussion, but yeah, I want to note that this is transferred properly. So this became S plus 6. And then it became S plus 6, you can write it as S plus 3, like that. Okay, so this is the S plus 3 But I would like us to add one more term here. I would like us to add s plus 3. Oops, okay. So I'm concluding our discussion. Just note. So it's going to be s plus 3 plus 3. Okay, there's one more 3 there. That came from that, but we're dividing by the same denominator. So here, but you're going to take the inverse, Laplace of that. You also will include it there. You include it there, which means that this one is fine because that's the plus 6. So this is going to be theta of s is 4e to the minus 2s divided by s plus 3. You square it plus 1. And then this one is s plus 3. You just split it up because the table will require us to have this, to have it like that. So here you would have everything like the Heaviside step function of t minus 2, the sine of t minus 2, and then plus e to the minus 3t cosine t. And then I would like us to add this last one, L of 3 over s plus 3, you square it, plus 1. Okay, so obviously, as you've seen from the thing, yeah, but also from the table. Once more, from the table, once more. See, okay, so you're gonna have the plus 1 there. It is exactly like how? This is exactly like this one. So it is theta of t plus 4h of t minus 2, the sine of t minus 2, plus e to the minus 3t cosine t. So now this is 3. Okay, so this is going to be minus 3t because you just put the minus there. Okay, so it's going to be minus 3t. Okay, that's the end. This one. Right, so in particular, it is the one with the plus. So it's exactly this one. So it's e to the minus 3t, the sine of 8t, which is the sine of 3t. So that is the answer to that question we're doing now. How do you check the answers? In general, you can check the answers by multiplying out, by evaluating the function of these values, just the initial values. So you would have, yeah, but that's the method. Like you can have this one. Okay, you can check theta of 0 must be 1, and also theta primed of 0 must be 0. Okay, so those are the kinds of things that you can do to check the two answers. But otherwise, obviously, this is the solution to that one. And yeah, right. And again, where am I? Where are we? Right. So where are we? We're here. Okay. Right. So we actually need to practice a little bit more. I need to put some questions that we can use to practice. Like, let's practice with some of the things. Like, any question?
No, just saying, please, can you give me like some more questions to practice on my own? Maybe I can come to you when I'm done.
Yeah, that's fine. There are lots of them. I'm looking at them now. So I'm gonna load like a lot of questions for you to practice. Like, here's an exercise. Okay, here's an exercise that I can give to you. This one. I have hundreds of them, but yeah, let me just write this one here. An exercise. An exercise. Right, so this exercise number 1, it says solve. Solve this one, y double primed minus 6y primed plus 9y is equal to t squared e to the 3t. And the initial values are y at 0 is 2, and also y primed at 0 is 17. Okay, right, these are exercises. But if you do this correctly, okay, because I've already done this, the solution to this one using the Laplace transform must be y of t is equal to 2e to the 3t plus 11 t e to the 3t plus 1 over 12 t to the 4th power e to the 3t. So if you do this correctly, you must get to the answer in red. Right, so there's another one, a bit very involving, but worth trying. This one here, number 2, you must be able to solve. So I'm going to give lots of them. This one is the second derivative of y plus 4 times the first derivative plus 6y is equal to 1 plus e to the power minus t, which is y of 0 equal to 0, y primed is equal to 0. Right, so if you do these very, very correctly, you will get the following answer. Yeah, because I've already done this. In other words, the answer is the following. So it is y of t is 1/6 plus 1 over 3 e to the minus t minus 1/2 e to the minus 2t cosine of the square root, e, which is the square root of t. Now this one is the answer to the blue one. So it's very important that you sort of understand that. Okay, I want to speak about other things like your basics. There's some basics I want us to learn on the Laplace transforms. Right, so, but these Laplace transforms can be learned from the basics. Let me give an example. First things first, what is the definition of a Laplace transform? Normally they don't ask that, but it's very important that you know what a Laplace transform is. For example, what is a Laplace transform? So I'm going to look at the definition. Okay, I know that we have discussed the Laplace transform, but let me give a formal definition during this discussion. The definition is that of a Laplace transform. What is it? Okay, because they don't ask that because they know it's very obvious. So to define a Laplace transform, we begin with a function. So we let f be a function. Be a function that is defined defined 4. Okay. Right, never mind. That's good. I can get to a larger screen. Okay, let f be a function defined by, I wanted to say defined 4. Right, if a function defined for t larger or equal to 0, then the integral. Right, so there's an integral, so the Laplace transform is defined as the integral of f of t, which is the same as the integral from 0 to infinity of e to the minus st f of t dt. This, if the case, is said to be the Laplace transform of f, provided that the integral converges. Okay, so this is what the Laplace transform is. This thing here. L of t, so if a function where t is greater or equal to 0, the Laplace transform is the integral there of integral of e to the minus t times f of t dt, evaluated from 0 to infinity. Right, so just a little bit of a note. There's a bit of history to this, and in terms of where it came from. We note that very quickly. I'm not going to waste a lot of time there. Before I look at just some basic examples you need to learn for assessment, the Laplace transform is actually named in honor. There's a mathematician that this is named in honor of. It is named in honor of the French. It is named in honor of the French mathematician and mathematician, named in honor of the French mathematician and astronomer 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 like Pierre Simon Maquis, okay, with an S, but it's French. De Laplace. This French mathematician and astronomer lived in the years 1749 to 1827. So he spoke French and he came up with this. So, okay, why am I stating these things here? I'm stating these things because it's very important to understand where these things are coming from. But it's not all about tables at the end of the day. The tables themselves are derived by people, but people who first learned the things from first principles. I want to discuss the first principles of this notion. Right. So I want to discuss the first principles of this notion. Right. So what are the first principles of this notion? Here comes a problem. In other words, you note. One note that is very important is that if you have the Laplace transform of a small f of t, f of s, the Laplace transform of g of t, g of s. So we just make it capital. Like small f, the L of small f, it's big F. Okay, so L of small y is capital Y. uppercase. So when you do the Laplace transform of a small y, it becomes capital. And this is consistent with the tables that we used. Okay, but I want to also mention, I want to give some basic example. Okay, what about if you do not have the table in front of you? How can you do this? If the question says evaluate the Laplace transform of the number 1, what is the Laplace transform of 1? We said it's 1 over s because we used the table, right? Yes, we said it's 1 over s because we used the table. But
Yes.
we can still do without the table. What about if we don't have the table? The truth is we still can be able to do it without the table. Like we can say, okay, we can say the Laplace transform of 1. These are the steps from first principles without using the table. Okay. We first write the formula. So we'd say, okay, we're looking for the Laplace transform of 1. And then we say, okay, first, what is the formula for the Laplace transform of any function? Any function. So it is the integral from 0 to infinity, e to the minus st, and then we have the small f dt. And then now we then say, okay, because now we can do this, let's ours continue to learn this when we are in a position to do this. Okay, that's fine. So we can say, okay, let's do the Laplace transform of 1 using this formula. So using this formula, so this f is 1, and then you put 1 there. So it is the integral from 0 to infinity, and then we have e to the minus st, and then you put 1 dt. So this is the 0 to infinity of e to the minus st dt. Okay, so we're just practicing with the basics of this. So what is this here? So this one becomes the limit. So from the integral, you introduce the limit as b approaches infinity of the integral from 0 to b e to the minus st dt, right? So what is this, right? So this here is the integral, so it becomes the limit as b approaches plus infinity. And this integral here becomes what? What is this integral here? So this is e to the minus that. Okay, so the laws of integration apply here. So if you integrate these, you just look at the coefficient of the t, so you divide that by the coefficient of the t, which is minus s, for the e function. And then now you can use substitutions like your e substitution in calculus to do this. And then now you evaluate this. So what is this? This is the limit is b approaches infinity. So what is all these stuff here? So you substitute. So if you substitute this, you can leave 1 over s outside, and then substitute the bs. So in the place of t, because this was the integral in terms of t, in the place of t, you put the b, and then you minus e to the minus. In the place of t, you put the 0. Limit minus 1 over s. So which is e to the minus bs minus 1. Okay, this is the answer we get, but what is this? Right, so you have minus 1 over s. So e to the, you put the b minus infinity s. So which is minus 1 over s. The infinity is like 1 over e to the infinity. Okay, 1 times infinity is, infinity by s is what? Infinity by s is infinity. I'm trying to show some steps, trivial. E to the infinity, infinity raised to, e to raise to infinity, like a number raised to infinity. Like 2 raised to infinity. Because e is 2 point something in mathematics. It's a constant. about 2.7. All right, so if you raise it to infinity, then it becomes infinity. If you divide 1 by infinity, it's 0. And then this is 1 over s. So the conclusion, therefore, at the end of the day, is that the Laplace transform of 1 is 1 over s. Okay, people have done this, and we don't need to be doing it all the time because it will take a lot of time to always be, when you're supposed to just evaluate the Laplace transform of 1, you must just know it's 1 over s because the steps are a lot. You can't just be doing all these steps. Otherwise, one calculation is going to be Bibles and Bibles of steps. You don't need that. Okay, what about some Laplace transforms of this? Let's do the Laplace transform of t. Okay, the Laplace transform of t would be the integral from 0 to infinity. You always put e to the minus st, and then the function f, you put it there, dt. Well, I'm saying these because we said that the Laplace transform of any function is the integral from 0 to infinity, and then we put e to the minus st, and then we multiply by f of t dt. This is the formula in green, and then now I want to just find the Laplace transform of this. Okay, some of this will require integration by parts, like this one is going to require something called integration by parts to do the integral, because now you have a function of t times a function of t because the st there. So integration by parts says the integral of u dv equals uv minus the integral of v du, but it's not really quite popular that integration by parts would be necessary for the students in the course in these courses to do. But yeah, in pure mathematics, the students learn this one in first year, and then now you can obviously be able to do this by integration by parts. But I want to elaborate on this very quickly and say the Laplace transform of t, for example, would be for there the limit as b approaches infinity of 0 to b of e to the minus st dt. Okay. Right. I can pick some colors here. Okay, that's fine. So, after I got this, what is then the integral of this? So we're gonna do the integral. So the integral is gonna be, according to this integration by parts formula, is gonna be u dv. So the idea here with the u dv method, I'll just elaborate very quickly so that you just can get back up on this, but this is not normally very necessary just to learn this some of these integration by parts, but it's going to be used many times in the derivations of this the table rules. Right, so u dv, now you need to choose here which one is u here, which one is v. E to the minus t, the t, dt, which one is u, which one is v, so that you can be able to use integration by parts. Okay, the trick with the integration by parts, if you make the wrong choice of the u and the v, you don't make an easy choice, then the integration is not going to work, it's going to be too complicated, and it's going to waste a lot of your time. So that is the trick at first year. Sure, you came across that. So now you then say, okay, it comes out, it pitches up here, and then you say, it's easier to say u is t. And then if u is t, then dv is everything that remains, okay? U is t, then dv is everything that remains. So it's e to the minus that dt. This is going to work because if you find the derivative of u with respect to t, the derivative of u with respect to t is 1. Why is it 1? Well, because it's t to the power 1, and then you subtract there by the power rule of calculus, which means power rule of differentiation, and this is 1. Okay, and then from the dv part, you want to find v, so you integrate both left and right, dt. This video is being recorded, so you'll have access to all these things. And then this here, if you integrate this one, it becomes e to the minus st. You divide by minus s, and that is exactly the v. So which means du equals dt. Okay, we got du, we got v. I'm just demonstrating how to find the Laplace transform of t. All right, I know it's taking a bit long. Right, so now with this here, okay, this integral of the dv part, this one, you can use substitution in calculus to verify why the s is coming to the bottom of this in green. I'm just mentioning that, okay? But now, okay, so we have everything we need. So we'll say, okay, what is actually the integral? So you leave the limits out in principle in calculus. You leave the limits out and to do the integration part, and then say, but this integral, what is it? This one. So you then say, what is the integral of e to the that? Right. So this integral here is equal to what? It is equal to. So you then say, okay, I'm going to use integration by parts. U dv is equal to uv minus the integral v du. What is u? U is t. U. What is v? V is this one. So it is e to the minus st over minus s minus. What is v? V is e to the minus st. Goodness me. dt. dt becomes what? Becomes du. du becomes dt. Doesn't matter. But yeah, dt. So here you have du, it becomes dt. The integral here would become, therefore, minus t over s e to the minus st, and then you plus here 1 over s. Okay. One step at a time. Negative by negative is plus, is 1 over s. And then you integrate again the e to the minus st, which becomes e to the minus st, and then you bring the t down. This is actually telling us that the integral of e to the minus st t dt, this integral is the same as minus t over s e to the minus st. Okay, not writing, this is not tidy. E to the minus st minus 1 over s squared minus 1 over s squared, like that. Okay, minus 1 over s squared, e to the minus st. Okay, that is sort of what one gets there for the integral of that, right? So that is what we get as a matter of fact. That's what we get as a matter of fact. Okay, you look at this and you think about it and see what these become. Right, so you get this integral here and you in business. So after this, you then say, okay, I've got these integrals. So which means the Laplace transform of t is actually the integral from 0 to infinity of e. We always write e to the minus st because I put in the block here, because the integral of f of t, the Laplace of f of t is 0 to infinity e to the minus st. F of t, this is the formula for the Laplace from first principles. So obviously f is t here, so you have this. What is this? You always put the limit. B approaches infinity, 0 to b. You always use the b part. B is popular in the calculus material, in calculus textbooks. You have e to the minus that. So just write the limit of b as b tends to 0 dt here. Okay, so this is the limit. B approaches infinity. So what is this limit? What is this integral here? So this integral becomes this. So this integral becomes this one. So it minus t over s e to the minus st minus 1. Okay, I'm concluding, please. Yeah, I'm going to give you a couple of more exercises to do, but basics so that you develop your prowess to deal with these from first principles without looking at the tables. Okay, but obviously we need some mathematical rules like integration by parts and the trigonometric, because you can do the Laplace of the sine, cosine of the trig functions. Okay, so I'm just copying the integral, the one in called in blue. So it is this one. Okay, so we have this. So which is the limit? Or you put the b, e to the minus that, minus 1 over a squared, e to the minus sb minus. So you put the 0 in the place of t, it's going to be minus 0 over s, e to the minus s. 0 in the place of t, you put 0. So wherever there is t, we put 0. And this is what we get. And then we have the limit. B approaches infinity. Okay, so let's see now. So let's see what we get. So this one would approach 0. Minus b over s, e to the minus is that, minus 1 over s squared, e to the minus sb, plus 1 over s squared. And this is 1, the e to the minus that, e to the 0 is 1. E to the minus 0 is 1. So anyway, so you get this. Okay, you take the limit as b approaches infinity. So wherever there is b, you put infinity. So this is going to be minus infinity over s, e to the minus e to the positive. Okay, e to the positive infinity here, minus 1 over s squared, e to the s infinity plus 1 over s squared. Right, so s to the infinity, s times infinity, so this one is going to tend to 0, and this one is going to tend to 0, and then you're only left with 1 over s squared. Okay, because the denominator is very, very large. Infinity is very large, so the denominator becomes infinitely large, but larger than the denominator. So here, if you divide 1 by infinity in mathematics, the result becomes 0. So only left with this. But why have we done all this? Well, we did this because we wanted to show that this is the Laplace transform of t is 1 over s squared. But I mean, it's pretty straightforward. You should have used the tables. Yes, we're just practicing now. And then now I'm going to give you some exercises that we can use to learn this. Like they give you there. Okay, they gave you the first question in the assignment. They said, do the Laplace transform of 1 minus. Okay, they gave f of t is 1 minus cosine omega t. It was something like this. So obviously, you just need to know what the Laplace transform of 1 is. Okay, we have seen that that one is 1 over s. We showed that just now. And with the interest of moving forward, I'm not just going to scroll back to that because we did that. But also, what about the Laplace transform of the cosine or sine or tan, any of these functions that you know from trigonometry in school? We can do this, but let's practice with this. Okay, the easiest one to do, let's do an exponential function. They can ask you this one. So yes, they can be obtained from the table, but if they ask you e to the minus 3t, what is the answer to this? Okay, we know that the Laplace transform of f of t is 0 to infinity, e to the minus st, f of t dt. Okay, this is the formula for the Laplace transform. So we know this. But what about if f is t now? It's e, excuse me, which is e to the minus st, e to the minus that dt. Oh yeah. Okay, so we have this. I'm finishing, please. Right. So here, this one is easy for the exponential functions. You don't need lots of integration rules because now you have the base e, so you add the exponents. You just combine the exponents. Okay, one is s and one is t. Which one is which? st 3t. This one is t. Excuse me. Okay, so you get this, and then now you have 0 to infinity, e to the, you can pull out the minus t, and then you're left with what? Okay, you're left with S here, and then you're left with 3 there. Okay, dt. This one is the limit b approaches infinity, 0 to b, e to the minus that s plus 3. Okay, I'm just saying how we can do this from first principles, but yeah, we're going to use the table a lot. I must indicate that. Okay, we have this, but you still can do without it. Okay, you have this. What is the integral of this? The integral of this, you just take the coefficient, so it becomes e to the minus t over s plus 3, and then you divide by minus s plus 3. I don't want to keep you here for too long. So you have b. Okay, you integrate that, and then after this, you get something. You get the limit b approaches infinity, and then we have minus 1 over s plus 3, which is e to the minus b, s plus 3, e to the minus 0. You have this one, and then you have minus 1 over s plus 3, and then you have e to the minus b, s plus 3 minus 1. Okay, so you take this when b approaches infinity. When b approaches infinity, the e to the power negative will always approach 0. And then if this one approaches 0, you are left with minus 1 over s plus 3 into minus 1, which is 1 over s plus 3. What is the meaning of this? Well, we've just proven that if you have the Laplace transform of e to the 3t negative, this Laplace transform is 1 over s plus 3. Okay, there's a table, obviously. The table says e to the maybe at is 1 over s minus a. So or something like that, or the table can be written in many ways. You can write if it's minus 80, if the a is negative, then it becomes plus, something like that. Okay, is this the slide that has the tables on? Not the one that has the tables on. Okay, is the other one, I think. Okay, yeah, is the other slide that has the tables on. Okay, to conclude my discussion, I refer back to the table again. And now let's see, refer back to the table again. And then I'm going to open, yes, the table. So would remember the table there. Okay, we're just concluding our discussion. So, right, so let me see what we do now, what we do now, what we do now. Right, let's see what we get. Right, so let's see what we have here. Okay, right, so let's go to the end. That's where I was. Okay, I want to just compare the tables. So you have e to the bt, for example. E to the bt is 1 over s minus b. So in other words, the Laplace transform of e to the bt. Okay. Okay, it's this app now. It's typing. It activated the text mode. So you'll just forgive me there. It's not doesn't really matter what this is doing. But yeah, I was saying if you look at this, the Laplace transform of e to the bt, okay, using the tables is this one. But yeah, in the exam, you're expected to also do without to tell exactly what the Laplace transform is. So yeah, you can just, but you didn't need to learn a lot of things. For example, let's use the table to practice because the table will always be there in the exam, but you still can do without it by using the formula I've just given. But what about if they give you the Laplace transform of sine 2t? How do you do the Laplace transform of sine 2t? Like we can do the Laplace transform of sine 80. What is the Laplace transform of sine 80? So the Laplace transform of that one is going to be a. So you write down the formula. The Laplace transform of sine 80 is equal to a divided by a squared over a squared. So if it is 2t, you put 2 divided by a squared plus 2 squared, okay? Plus 2 squared. Plus 2 squared. So in other words, this Laplace transform is going to be exactly 2 divided by a squared plus 4. Yes. Okay, so we can do some other Laplace transforms. What about if they give us the Laplace transform of, find the Laplace transform of something, something, something. Okay, let me just give this exercise here. On purpose, they can give you the Laplace transform of 4 to the power 5t minus 10, the sine of 2t. What about if they give us this one? Okay, and then they say find the Laplace transform of this. So the Laplace transform of this, you need to know that it's linear. Linear means it goes into this might be just the last one, and then I'm going to give you an exercise. It goes inside the sums and differences. So you'd have 10, the Laplace transform of the sine of 2t, and then is 4. What is e to the 5t? So it becomes 1 divided by s minus 5 minus 10 into the Laplace transform of sine 2t is 2 divided by a squared plus 2 squared. So this Laplace transform is 4 over s minus 5 minus 20 divided by a squared plus 4. Right, what have we done now? We've just showed that the Laplace transform of this one here, the Laplace transform of this is exactly that. Right, the Laplace transform of 4e to the 5t minus 10 sine t is that. All right, now let me give you some exercises because you need to practice during your own leisure. And then I'm going to give lots and lots of exercises. I have lots of them here. I'm just going to type them on the screen. So you're going to see them and be in a position to practice and make sure that you learn. Okay, here are some exercises. This is a good list of exercises. Maybe I give 10 of them. Okay, like a bit lot. Right. If I give 10 of them, like number 1. So the question is find L of f of t. Right. So you number one. Number one, we can ask you to find the Laplace transform of this one, for example. F of t equals 4t squared minus 5 the sine of 3t. Okay, so okay, that's okay. I want to give even basic ones, like they can ask you to find f of t equals e to the t plus 7. F of t is e to the minus 2t minus 5. F of t equals t e to the 4t. F of t is t cosine t. F of t is t sine t. F of t is e to the t cosine t. F of t is t squared. Okay? f of t is 2 squared plus 6t minus 3. F of t is cosine 5t plus the sine of 5t. Okay, I've already solved all these problems, but I'm just sharing them. But yeah, a lot. Okay, maybe I will give you this. And then I give you the hyperbolic functions. You can trouble you with this a little bit, so you need to practice it in advance. What about if it's the sign, but the sign that is like h is called the stinch? Hyperbolic functions. So you can also be given f of t, which equals cosh. This is not cos, but it's cosh. Kt is called a hyperbolic function. And they know they can give you 13 t. What about if they give you e to the t, the hyperbolic sign of t? F of t. Okay. I'm going to stop. Okay, is that f of t equals e to the minus t cosh t? Okay. Okay, here we say by first using the trigonometric identities. So find the Laplace transform L of t, L of f of t by using first a trigonometric identity cosine 2t point 3 plus 5 15.4. Now you need to use some trigonometric identities, most of which are from school, metric, etc. First year, second year, those things that come, those trigonometric identities that are used in integration and differentiation. There, so you have this. All right, so we're done. Okay, so yeah, so thanks a lot for joining us today, and then we'll talk again. Okay.
Okay.
Yeah.
Thank
Yeah. So
you.
thank you. Thank you.
You
Yes.
you're gonna send the link to the recording, right?
Yes, I'm gonna send the link to the recording in like 30 minutes. Okay, it takes like 30 minutes. You know, it takes like 30 minutes for the link to appear because the link is sent to me by Zoom on my email. But now Zoom takes like 30 minutes, an automatic thing, but it takes like 30 minutes to send the recording to my email so that I can send you the link to it, you know? Yeah, it should take like 30 minutes for the link to appear because it's not that I'll just have the recording now. I'll just stop our lesson and then Zoom after 30 minutes sends me the link to the video, the recording, and then I can send it to you. Okay.
Okay,
Okay,
that's
thanks a lot,
fine.
dear. We'll talk then. Goodbye. Okay, thanks. Goodbye.
Okay, bye.
Okay, goodbye.